Yep, let's go.
Done. Okay, great. So, Tudor, please start your third lecture on the title, which is on your first slide, please.
Great. So my plan was to say the last things about BPS states and those connections, and then if there's time, I'll say something about 3D holomorphic topological theories. Um, in terms in terms of what's coming, the things we've been doing in 4D and BPS states from, I guess, from my perspective, are interesting because they're connecting some mathematical concepts that already exist to computations in 4D quantum field theory that did not exist. For example, like hands-on computing a CoHA in terms of fields and Feynman diagrams and such in 4D field theory. Um, and getting some conjectures for structures that should exist on this. Aside from sort of reorganizing expected structures, I'm not sure so far that there is a lot of really new or surprising math coming in. For me, the connection is really the new thing is connecting to the physics. I hope that there will be some new things coming in as the computations are pushed further. The second part of this in 3D is kind of new from both sides, and there are, at least to me, some surprising algebraic structures that have appeared even on the math side that I don't think people have really thought about. And if I'm wrong, I would love to know and to explore. Um, so 3D is where some strange DG structures start appearing in Yangian-like algebras. So that was work with Wenjun, and there's a paper out on that. So I'm mentioning this because if you find yourselves getting bored in the 4D section, you can just tell me to hurry up, and I'll maybe throw some new algebraic structures out in 3D. Um, so last time I mentioned 4D holomorphic topological theories, and that line operators form a chiral E1 category that has multiple definitions or quasi-definitions that are supposed to be equivalent. The sort of working definition that I use um, is just involves looking at a collection of categories, one for each point in the transverse dimensions, C times Rx, with products coming from separating points, either topologically or holomorphically, um, and a compatibility among the products, and also I should say their translation isomorphisms relating all of the different points. And so if you want something minimal, you can just focus on a single category at zero, and then when constructing these products, just translate it to other points. Um, then the hammer we tried to hit this with was constructing fiber functors through boundary conditions, and then doing computations of the analog of what I called spark algebras in the first lecture, um, computing the endomorphisms of these fiber functors in terms of physical fields. And that's the part that's black boxed in this talk. I'll describe some consequences of that. So One of them is when there are boundary conditions like this, the expectation is that the algebra that arises as endomorphisms of the fiber functor splits as an algebra into two halves, just like in a Drinfeld double. Should say here, Jan has, in one of his papers, tried to define Drinfeld doubles like this, I think. And I would love to know how that definition coincides with what we're finding here. It has not been obvious to me. Um, um, so, so each half is a vertex by algebra, meaning it has a product and a vertex coproduct that is potentially singular. And that structure comes from separating lines in the holomorphic direction. And a priori, there is a different honest non-vertex coproduct that can be translated to look vertex-like, but regular, coming from separating lines topologically and throwing in another pair of boundary conditions to separate them. And the second one has a non-trivial R matrix. The first one should be symmetric. And these things, because at the end of the day, they both involve the same configuration of lines in C times R2. There's got to be a coherence between them, which translates into a Drinfeld twist.
So
And so the
should we think morally very naively that you have two Hopf algebra structures compatible with each other?
yes, so if they were honest Hopf algebra structures, then the compatibility would amount to a braiding.
Mm.
And here one of them is not an honest Hopf structure. It's got a vertex coproduct that doesn't make sense when the parameter is set to 0. And what then the compatibility involves a meromorphic braiding. It's somehow, oh, sorry. Yeah, sorry, that's fine. Oh, so yeah, exactly what you pin down and where you put your coherences gives you different descriptions of the structure. I'm giving something that is, in this setup, minimal. You could ignore the holomorphic coproduct. But anyway, let me just summarize again. So what you end up with is sort of two structures that look nearly the same, that in this case are related by a twist. And because of the existence of these boundary conditions, they're rather a consequence of what I'm calling the existence of the boundary conditions. One of the products, the OPE holomorphic product, has to be perfectly symmetric. The other one, the Hop product that has just been translated to have a holomorphic dependence, is not symmetric, it's braided, but it is regular when S goes to 0. And the coherence between these things implies that the R matrix, the spectral R matrix, factors in terms of the Drinfeld twist.
So it's sort of what Drinfeld call co-boundary Hopf algebra, something like that. I forgot. Because
Yeah,
it looks
sorry,
like
I've never
co-cycle
heard
is
those words, but it makes complete sense. Yes,
yeah. Okay.
Sorry,
exactly.
I have a somewhat related question. So usually in these R matrices, are always skew symmetric in the sense that like the one you write down clearly is a unitary. Um, and is that something that you always expect from any kind of Carroll Ivan Carroll out category, or is this some coincidence here?
Um, I feel like I want to say yes, and then I have to think whether there are some subtle framing anomalies that can enter that will screw it up. But even if you didn't have the left-hand side, knowing that R had to be factored, you would still need R to be unitary, um, just because crossing lines and then crossing them back should be a trivial operation in 4 dimensions.
I see. Thanks.
Um, um, yeah. So, um, so I wanted to connect this with BPS states by applying these ideas in 4D n equals 2 theories. Um, and so as a reminder, 4D n equals 2 theories are all described in the infrared by Seiberg-Witten theory, which means abelian gauge theory with some electric and magnetic matter. Part of the mathematical structure that appears there is a charge lattice that has twice the rank of what I'm calling the rank of the abelian gauge theory. It's got electric and magnetic parts and a symplectic pairing on that lattice. And of course, there's also a central charge that I'm not going to go into detail about here, though it is important. Um, and there's some collection of what physicists might call BPS states in math. They're typically accessed as cohomology of moduli spaces of some quiver. They correspond to stable, um, well, they correspond to moduli spaces of compact objects in some Calabi-3 category. They compactly supported sheaves. Um, and what a physicist typically calls the BPS state um, corresponds um, to the stable objects. Um, so there have been many hints over the years that BPS states are related to line operators, and giving a few that were particularly motivating for us, but they've appeared in many places. Um, one early hint, which is sort of early hint in terms of indices, which was upgraded algebraically by Gayoto and Kahn, is that there ought to be a Koszul duality between local operators in a 4D n equals 2 theory and a CoHA. And if you remember the sort of things I said about Koszul duality before, that the Koszul dual of local operators should be the thing that represents lines, at least perturbatively.
Yeah, I'm confused kind of a bit conceptually because when you say relation with BPS states, you mean some stability condition, but CoHA itself, it doesn't depend on stability. It's kind of, yeah.
That's correct. Um, I agree, but the way it is presented does. And so what I mean by BPS states depends on stability, but the algebra they generate, I guess that's what you showed. It doesn't depend.
Hmm.
Um, but the way computations are done does.
Okay.
Um,
Go on. Yeah.
um, so there was on the math side, um, the and I completely missed this initially. The fact that they're vertex algebra structures, or if you dualize vertex bialgebra structures on CoHAs, and coming from work of Joyce, um,
I
so
am not.
suggests.
No, I mean that if I remember, I mean this Dominic's paper, he did not really use, for example, the potential. I mean, it does not look as a 3D Calabi-Yau construction. That's maybe Alyosha. No, I think Latintsev gave a talk here. It's kind of, you use just the cohomology of the space, but you with its pairing, it
Without
already gives you sort of a free vertex algebra. Maybe they have upgraded it, but probably not in 18 or
oh
21, but
gosh, yeah.
recently. Yeah.
Um, yeah, thanks. I think you know better than me what cases it holds for. Yeah. Um, that I actually learned about this after we started doing our work, but I from looking at some very recent work of Latinsev's and Ben Davison's former students, Shivang Jindal and Sharunas Kobris. Um, they I might as well mention this now. They relate um, the Joyce's coproduct with Ben Davison's localized coproduct, which I think makes sense for critical cohas with superpotential. And this I will show in a few slides how that ought to fit into the 4D picture.
Hmm.
Um, um, and then there was work from 2 years ago on um, describing line operators as in terms of framed quiver representations and putting a CoHA bimodule structure on those and showing that that was compatible with expectations for products of lines where the tensor product is tensoring over it's the bimodule tensor product, tensoring over a CoHA.
Yeah,
Um,
we are trying with Rio, Fujita, and Yaping, Yang, and Gufang, Zhao to make it another way around, to give mathematical definition. You see, like similar
oh,
to
fantastic. Yeah.
Cautis and Williams, but starting with something like CoHA. Yeah, kind of
That
to invert. Yeah. Okay, but anyway, so it's
I've
indeed
I've
there
heard
is a lot.
various early stages of that. I would love to get an update.
I
Yeah.
mean, it's still maybe early, but it's more than 80 pages file. So it's growing. Yeah.
Yeah.
Yeah. Okay. Yeah.
And just also to mention some of your work that if you read it correctly lies sort of in
Uh,
this area.
line
I
operators.
so
Not
so yeah, of
sure.
course you don't talk about line operators, but
We wrote two papers, and one is rather this David AGT, sort of a generalization of AGT, vertex algebra. It's very mathematical now topic. You have cohomology of the moduli space of some representations, say framed quiver representation, and there is a vertex
absolutely.
algebra acting on it, but it's AGT type of statement. I don't know. Is it related
I I,
to
I
it?
think it I think it should be. Uh,
Maybe I don't know.
but I
David
would
is here, so maybe he
love to
can
poke
tell.
that more as well.
Yeah. Okay.
Um, okay, so again,
Yeah.
we wanted
Hi.
to
So, David, this your AGT story and the action of subsequent mathematical like co-action of CoHA on the modular, is it how it's related to line operators and to the category? Because I don't remember that we really used heavily the monoidal structure on anything. So
right. So first of all, because it's a quiver it's a symmetric quiver, which would not appear as a gauge theory. It's a story about string theory rather than gauge theory. So that's an immediate caveat. That, surveying string theory is not clear that you should really think about it as line defect as opposed to branes. But with that caveat, there will be no compact T-branes in. You're studying string theory on R2 times C times a Calabi-Yau cone, which is the equivalency tree. And you can try to understand this holomorphic-topological theory for dimensions. Now, for the connection to vertex algebras, you want to go one dimension higher to 5 dimensions to twisted in theory. So this 4-dimensional perspective gives you the vertex algebra as opposed to the chiral algebra. So the say endomorphisms of some line will give you the vertex algebra or something like that. Of the vertex algebra of the W algebra. Right, and you have different types of modules with different properties, which all look like lines in 4 dimensions, but sort of they have different origin in 5 dimensions. But otherwise, apart from these caveats, the shifted affine Yangian would play the same role in the story as the Yangian is playing in this story here. Of the
Yes.
okay.
And presumably one could perhaps try to identify the CoHA with half, no, not perhaps. I don't know the bimodule perspective very well, but perhaps one could try to establish a parallelism. Try to think about modules of the vertex algebra as bimodules for the positive part of the vertex algebra. I don't know if it's a useful thing to do. So anyway, sorry.
Okay. Yeah. All right. Thank you. So okay. So Tudor, yeah, go on. Yeah.
Cool. Right. So we wanted to do some 4D computations and see how far we could push it. And so another black box is that there's a natural way to construct boundary conditions and interfaces in the Seiberg-Witten theory, and in fact the HT twist, compatible with the HT twist, that chooses an ordering. There are many choices to be made. They're the same sort of choices. It's exactly the same one when you're writing down a spectrum generator. You choose the splitting into BPS versus anti-BPS states, and then sweep across the central charge plane and look what gets picked up in a certain order. And each this procedure, which goes back, the essence of it goes back to some work of Chakotay-Netsky and Vafa. That procedure can be modified to produce boundary conditions that sort of kill one BPS state at a time as one sweeps across the central charge plane. BPS on one side, what I was calling N boundary, and an anti-BPS states on the other side in sort of the symmetric order, which is what I was calling D. On top of that, we can actually get an absolute fiber functor to vect by choosing an electric magnetic splitting of the gauge group, or choosing what you mean by electric, and putting Neumann boundary conditions for the electric gauge fields on one side and Dirichlet on the other, which also means Neumann for the magnetic. So the upshot is that there's a hierarchy of interfaces or boundaries that can be sandwiched together to get an absolute functor. From the very outside, what one obtains as an endomorphism algebra is something that represents line operators in pure abelian gauge theory. And one computation of that is the Countess-Williams category associated to GL1, and here it's GL1 to the R. And it's not hard to show that the thing that represents it, first the fiber functor I'm talking about is global sections on the affine Grassmannian, and what represents it is a non-perturbative extension of a Yangian for T star GL1. I'll describe it in a second.
That's true not only for GL1. I mean, that's at least that's
Right.
what we try to show.
So well, some things are true and some are not. So perturbatively, if you work with the Lie algebra, a statement like this works for any G. The problem is that the fiber functor you build isn't faithful for non-abelian groups. What I used to call a completeness condition is not satisfied. So you don't actually represent the entire category. You represent some small piece of it, but then there are ways to correct it that possibly, remembering discussions with yapping, you might already be using. I think the issue is that global sections isn't a fiber functor, but if you introduce line bundles, then
Yes,
then you can fix it.
That's what's happening. Yeah.
Fine.
Okay.
Great. From the inner boundaries, or rather from the interfaces on the inside, one gets algebras generated by the BPS states in at least locally in a computable way. And the structure has to fit together compatibly. In particular, the two BPS algebras have to be algebra objects of the right type, which here means vertex bialgebras inside modules for the abelian part. And
should I think about this as an analog of this finite dimensional story where you have enveloping algebra of Cartan and two halves belong
yes,
to
where the upper and lower nilpotent they form algebra objects.
So then in the end you get it's not just CoHA, it's double of it.
Exactly.
Okay.
And so the complete algebra has CoHA, has it's dual in an appropriate sense, and the Cartan that's coming from the abelian gauge theory.
So gamma I is a basis for maybe 1/2 since it's symplectic of the lattice. It's a basis.
It's half.
Yeah.
Sorry, it's not a basis of the lattice. It's running over stable BPS states.
But probably one should expect that any object is an extension of stables in the end. So probably at the level of K-theory, the classes should generate the whole K-theory.
If you're talking about quiver representations, I think I agree. If you're setting this up in gauge theory, it's possible to just throw in electric matter. In fact, it's the nicest thing to start computations with, where you just don't have magnetic states, and they don't generate the lattice. So just they're natural generalizations outside of that.
Yeah.
So one conjecture, like this is a different computation. It's not at all obvious to me a priori how it, well, there are clear expectations, but it's not at all obvious a priori how it's related to this standard sort of structures on the CoHA, and so it will actually leave it as a conjecture, but a very strong one because it has all the same properties that this HBPS is the CoHA. And then from this sandwiched picture, we expect the following hop structures. If we, it depends what monoidal equivalences we build by sandwiching together the various boundaries and by using completeness versus separating in the holomorphic direction and just annihilating the boundaries. And depending on what one does, one gets different coproducts that are related by Drinfeld twists. So the expectation is that there's a fully symmetric coproduct that is however singular that that is related by a twist to a slightly less singular coproduct, which plays the same role as the deformed Drinfeld coproduct in the classic Yangian, which is not quite symmetric, but uses the R matrix of the abelian part to swap it. And then there's a third step that should use a Drinfeld twist built out of the BPS states to relate that to a regular coproduct that has some quite interesting R matrix. And so the second conjecture is that the thing in the middle is what shows up from the work of Joyce and Davidson that Latintsev and Jindal, Kalbris, and Latintsev have been sort of spelling out in greater detail recently.
So you mean sort of meromorphic coproduct structure or what? Because
that's right. So this is a meromorphic coproduct that uses the abelian R matrix in to relate it to its opposite. And I say that this matches in large part by comparing formulas with what Latintsev and company have been doing. So the part that I feel fairly confident in actually doing physical computations of are the first two steps. The last step is hard, and we can do computations when everything is electric or mutually local physically, and there's a naive expectation that involves spectrum generators to compute that Drinfeld twist that hasn't been working yet. I think it should be extremely interesting to work out, and actually figure out how to get to the regular coproduct. And I've got some formulas to the extent that people would like to see them. maybe I'll show some formulas and then see if there are any questions. So I say here that I'm restricting to acyclic quivers. I don't think that's necessary except for a certain step further down where I need some things to commute. I'll get back to that. But so there's sorts of theories, just examples of what I have in mind are simple quivers like this. And I would say the first one in a stability chamber where everything's rigid has two BPS states. And in fact, they both have two BPS states, but the symplectic pairing between them is different. So to give an example, I need to pin some things down. So the charge lattice has electric and magnetic halves that are naturally dual to each other. They're the character and co-character lattices of a U1R. Describing them that way requires a choice of a splitting, but there is always a choice of a splitting. And because the two halves are dual to each other, there's a natural symplectic pairing. And I will need, for the inverse of a pairing, which I can think of as a canonical element in gamma tensor gamma, I need to split that into sort of two halves. There's one half that involves electric times magnetic, and there's another half that involves magnetic times electric. And so omega plus inverse is what I'm calling the electric to magnetic part. That's, yeah. I need that to start writing down any formulas. And so in a chosen basis of the charge lattice, this canonical element just uses the inverse of the symplectic pairing. And right, so the abelian part, which is the same as this cartan that's appeared in math, has some totally commuting generators.
So abelian part, do you mean infinite Heisenberg algebra, or you do not have this central charge? They all commute.
No, yeah, they all commute.
Okay.
And it's also, yeah, it's not, it's different.
Yeah, it's one half.
Algebras,
Yeah,
because it's only one half.
Yeah, one half.
Yeah. So it's positive modes only. Just for the Yangian. The part that is weird and that I'm calling non-perturbative is that on one hand, the zero mode is constrained to the representation theory we care about, had a category on which the zero mode acts semi-simply with integer eigenvalues. If I didn't impose that, then the algebra I wrote down would need to be much more complicated. So this is an easy thing to do for abelian theories. And the way these sit in generating functions is also a little strange. It involves logs, or if you exponentiate, it involves alpha, the z to zero mode power, which is something that is easy to write down in formulas and in relations, but then if you're really looking at what's going on, you need to sort of always evaluate that on modules within a fixed eigenspace of the zero modes for the formulas to actually make sense.
And what is this Ka, where it comes from?
So what I didn't write down a physics formula, so it comes from an integral of the gauge fields along a copy of C that is sitting at a fixed time on one of these boundaries. That's twisted a bit by, yeah.
Okay. It's computers.
Yeah, so this part I am happy is complete straightforward computation.
Is that some called a logarithmic vertex algebra, or especially with
Well,
this?
it's the same. No, it's not logarithmic in the same way that people say logarithmic in vertex algebras, I think. But it's the same phenomenon that appears for just a free boson for the Heisenberg. When you're constructing Fock modules for the Heisenberg, the vertex operators that generate the modules involve a formal integral of the Heisenberg field. And it's that formal integral that's actually appearing here that's playing a fundamental role. So there is certainly a close analogy to that.
But you don't have the logarithmic term here.
Yeah.
Generating fields.
So it's yeah. So if you want, you can think of it as simply a bookkeeping device, and then check that everything makes sense. But there is a genuine reason for it to be there. Let me say physically what's happening. The reason that logarithms appear is because there can be both Wilson and 't Hooft lines around. They're line operators with electric and magnetic charge that can appear. And when they both appear, they're branch cuts around.
Yeah, because you have the co-multiplication with the parameter s here, which looked like
absolutely, yes.
And which looks very much like Lapowski and Huang. They do this called a logarithmic tensor products or fusion products. So that's why I was asking.
Yes, I think that's similar. Sort of similar. Let me emphasize that in this coproduct formula, there is no log of S. This is an expansion in S over Z. And so there are logs of Zs. Well, sorry, it's not even, it's sitting inside K, which has been exponentiated. But when you expand this, there's nothing funny about S. And this is just as regular coproduct in S. But the sort of effects you are talking about are prevalent everywhere, and there are branch cuts around that are physical and need to be, well, they're there for a good physical reason and need to be accounted for.
Okay, thank you.
Yeah. So just for the abelian part, the first two coproducts I mentioned, the one that's completely symmetric and the one that could be singular and not quite symmetric, they're identical. There is a Drinfeld twist that relates them, but because we're in a commuting algebra, the Drinfeld twist does nothing. The only difference is that the second one has an interesting R matrix and the first one doesn't. So the interesting R matrix, maybe also later write it in modes, has an initial term that has the zero modes. That's interesting and weird, and then stuff that looks like a standard Yangian R matrix. But so in particular, and I think so. I don't know if Davide is still around because I can't see the audience. I think over the years, every time I've talked to Davide about this, he keeps asking me about preserving spin. And at the end of the day, this does not preserve spin. There's no conformal grading on this thing, and there can't possibly be. And there are several ways to see that. But this R matrix itself, if evaluated in a non-trivial electric magnetic sector, has a spin that depends on the electric and magnetic parts. And it is what you would want for a good to preserve conformal gratings everywhere, or spin or loop rotation or whatever is for this to be invariant, and that just doesn't happen. And then there's a BPS part that's generated by E's and F's, and here I am heavily simplifying and assuming that the BPS states are all rigid, that the or spherical in terms of
Can I ask you a
dimensions.
question?
And they correspond to the vertices of the quiver. Yeah.
Yes, exactly.
Wait, can I ask you a quick question?
Yeah.
Is the Z grading a symmetry at least in one of the?
Yes, it is. It's in within each half. It's a symmetry as long as you as long as you twist appropriately when you commute things to change
I
the
mean,
spin.
you have three different.
But yes.
You have three different things related by these Drinfeld twists and stuff. Do you have rotational symmetry at least in one of those, or
no,
just
you
nowhere?
don't. The algebras themselves don't preserve it. So it's not a violations appear everywhere, but fundamentally at the algebra level, it's not preserved. And I'll show you in a second why.
But the theory is rotational and invariant, so somehow the symmetry must still be there.
I
in
agree.
some form.
I agree. It is incredibly hidden. Yes. It says the thing that used to frustrate you now frustrates me. However, the algebras hold together. So yeah. So it's anyway. So I'll explain a bit of what's happening. So there are relations between the abelian or Cartan bits and the E's and F's that that maybe look standard. That just involve the charges or expanding the BPS charges into a basis. And then and then there are exchange relations like this, and this is the first place where you immediately see that spin is going to be violated. So you get exchange relations between different E's and different F's. In this formalism from the following fact. When there is one BPS state per node, and those are the only stable objects, and I am assuming that now, there should not be any interactions between them. I don't think one can write down any, at least perturbatively, one can't write down any interactions.
You mean interaction between E's and F separately, or
I mean between different E's.
Yeah, it's from the perspective of CoHA, it's clear, yeah, if you impose this condition, yeah.
And if there's nothing else, then one expects everything to commute, but commute means inside a braided tensor category, or it's inside one of these meromorphic tensor categories. And so commute means with the abelian R matrix telling you what the commutation relation is. And so it's the R matrix that specifies that power of Z minus W on the right-hand side.
What I kind of missed, E and F, how do they commute?
I haven't written it.
You will, okay.
So these are the two halves separately. So one immediate violation of spin is that the powers of Z minus W are opposite. They're inverted for the E's and the F's, and together they're not. The rule for preserving spin is not going to be the same.
So it's CoHA and opposite CoHA, something like that.
Yeah. And then the computation that we do for the EF commutator is through Feynman diagrams, and it's a thing that is in your papers, Jan, and in Davide's papers, and the answer is not surprising, except that K has a leading term that's Z to a zero mode, and so this one also doesn't preserve loop rotation. I think what's happening here is that the situation in which it doesn't preserve loop rotation is when you have an electric spark, an electric algebra element on one side, and its negative, an electric thing on the other side, and a magnetic line going through the middle. And you're trying to move these things past each other vertically in time in the presence of a magnetic line. And that's going to change the spin, which is why the right-hand side has funny spin. Right, and then there are coproducts around. The symmetric one, again, is a direct computation. It is not obvious that this is singular. The poles that are being picked out in these contour integrals, and they have residues that involve lots of negative powers of S. And I've introduced some more notation here. What is happening is that the K's all go to the coproduct of E or the coproduct of F for each BPS state. It's one or the other. And the one that doesn't have it is just a standard like F tensor 1 plus 1 tensor F. That's what K plus and minus means. And the way that happens depends on how I've split my charge lattice. Which in turn is related to how I've defined the boundary conditions for the abelian theory. That's related by a Drinfeld twist to the, think of this, the Joyce-style or deformed Drinfeld coproduct. And darn it, the formula is slightly wrong. I thought I had fixed this. Sorry, it's fixed here, but not on the previous slide. So I'll give you the correct one. What the Drinfeld twist does is move K's around and collect them all together. And so it starts looking a little more similar between what happens to E's and F's. This is still singular, but it's not quite as bad. And this coproduct is order reversed by the abelian R matrix. The bit that is sort of most interesting is that one would expect this then to be related to a fully regular coproduct using a Drinfeld twist involving the BPS states. And I only know how to do that in, depending on your perspective, the somewhat trivial case of all electric BPS states. And so this is the thing that, Jan, that you didn't want. So if the BPS states are such that the symplectic pairing vanishes on any pair of them, which is you can certainly cook up in gauge theory, then the expected answer works. There's a Drinfeld twist just built out of E's and F's that makes the singular coproduct regular. And in the bottom, the reason it's regular is because now this is an expansion in S over Z everywhere. Has a good limit as S goes to 0. And what I don't know is how to generalize this. What I would love is to have a product of this FBPS expression in like central charge order looks sort of like the spectrum generator, but at least naively that isn't quite working yet. That would be really nice to figure out. Okay, that is all I have to say on this. Are there any other questions? And I had 2 minutes early, so.
Sorry, can I ask a question about what you were mentioning about the spins? Is this just a C-star loop rotation?
Yeah, it's a loop rotation.
What was the
That
point that?
isn't, it's not a symmetry here.
Well, I guess for U1 gauge theory, your fiber functor still works even if you use the C-star equivalent category. You just have your generator is just not symmetric monoid. Like the coproduct for your generator is not the standard symmetric coproduct, but you can still define a coproduct on this extra generator of the loop rotation. I don't see why.
Right, and I think that's not enough. I think that we'll do it for each half for HBPS and HBPS dual, but the two coproducts differ by a minus sign and they're not compatible with each other, at least in this setup.
Okay. Okay, thanks.
Sorry. Yeah, I wish I was giving you a different answer, but this is what we've ended up with as a structure that holds together. Cool. I have another talk, but I think you can just look at the slides. So
no, you can comment on the remaining part, because here what you just said, it's probably of great interest for physicists, but since all the computations are done
I did warn you.
Physics level, so for mathematicians it's just the answer can say something. Yeah, but what's happening after that, it's something of mathematical interest, so maybe you can browse.
I should say here, like I want to really emphasize that our conjecture that the Joyce coproduct can be conjugated to something regular using a twist built out of the BPS states. And I think there should be some really beautiful way to do that. And it would be nice to think about. But I'll finish there. I will flash some slides then on this, and I need to go in 15 minutes anyway, so it'll be short. So this is what I had planned for the third talk. I wanted to discuss some work I did with Wenjun and Victor P. We have a paper on from about a year ago, which is a situation that ought to be a lot simpler, and in many ways it is. So consider 3D theories with one holomorphic direction and one topological direction. So now line operators just form a chiral category, not a chiral E1 thing. And the same way as before, that one way to think of that is as a collection of categories labeled by points in C with translation isomorphisms and an OPE. Another good way to think about this category is the following. If you're used to vertex algebras, modules for what some people call a vertex operator algebra or vertex algebra with stress tensor, with conformal vector, form a braided tensor category under fusion and with some caveats. But if you don't have a conformal vector, there's, at least in some cases, there's a notion of fusion that Huang defined. But what you end up with is not a braided tensor category. You get something where the product of lines actually depends on holomorphic separation. And so the thing I'm describing here you should think of as representation theory of generic vertex algebras that don't have conformal vectors. Now the product there is fusion and is difficult. What I want to do is to use fiber functors to get products over vect, not fusion products when representing. So what sort of object would I want to represent this category? Naively, you'd look for vertex bialgebra, just something that just has this singular coproduct. And the surprise was that this isn't actually true, and it fails in a subtle and interesting way. The way it fails has an analog in two-dimensional topological field theory that I'm not sure is known or appreciated. I haven't been able to find it anywhere yet. And so I just want to mention it rather than doing the complicated setting. I want to do a simpler thing. And the idea is like this. Causal duality relates E1 algebras or A-infinity algebras to other E1 algebras. And if you start out with an E2 algebra that has two E1 directions that should be compatible with each other, you can just dualize one of them, and you get familiar statement that so in the version of causal duality that I am using here, there's also a linear dual being applied, which means that if you dualize one of the directions, the product in the other direction dualizes to a coproduct. And so the causal dual ends up having both a product and a coproduct. And you would want this to be a bialgebra. And I think that is the standard expectation that the causal dual of an E2 algebra is a bialgebra, but it's not true.
No, I don't think
Maybe you're
so.
going to also tell me that it's not true.
No, it should be true. Yeah, it should be E3 structure.
No. It's not. It's very close to being true. The E3 thing gives you a braided, gives you a bialgebra that further has a braiding. It's not true for very subtle reasons. And it's not true because the two E1 directions, one of which I was dualizing to a coproduct, are the compatibility between them might be non-trivial, and the non-triviality is measured by a Gersten-Haber bracket in the E2 world. And if there's a non-trivial Gersten-Haber bracket, then that prevents the naive coproduct from being an algebra morphism. The good news is that that can be corrected. And the way to correct it is with a more Cartan element in the second tensor power of the dual that is constructed morally out of inverting the Gersten-Haber bracket. That's also not a good definition because the bracket can be degenerate. There's a better construction, but the claim is that one can correct the A-infinity structure on a dual tensor A dual by a more Cartan element to make the coproduct an algebra morphism.
But it's not the usual tensor product. Yeah, it will be tensor product in some generalized sense.
So it's a tensor product of A-infinity algebras deformed by a more Cartan element. Sorry, I should have written that. That's what I mean by tensor
But also
over
if
R.
shape is a G algebra, right? So you can use the standard tensor product.
If I have DG algebras, yes, but
Not saying a shape is always a DG algebra when it's presented, right?
What do you mean?
It's
not true.
defined by the bar complex, so it's a DG algebra. Then you can pass to cohomology, whatever.
I completely agree with that. When actually computing this thing in perturbative field theory, you get a smaller presentation than what you're thinking of, and it immediately has non-trivial A infinity operations.
Kind of totally lost. If you have an associative algebra which is DG, infinity, whatever you want, okay, how you make it into Hopf algebra, well, by algebra, I do not understand what's going on, frankly. So suppose I'm just reading what you wrote. So you have an E1 algebra. For example, associative algebra is an E1 algebra, all right?
Yes.
All right. So you
So
dualize.
suppose it has, no, so associative is not enough. So I need an E2 algebra. So I need something that is E1 in two different ways.
Okay. So, all right. So it's not just E1, but it's also E2 algebra. Good. Then probably you can make it this way. Yeah. Okay.
Where so the E2 algebra has two compatible products, and dualizing one of them lands you, like Koszul dualizing one of them lands you in, optimistically, in the Hop world, except it really doesn't.
Yeah, but what I mean that probably it's well known, but kind of I haven't looked at it for decades. If you want to define the Hopf algebra structure without antipode, which means bi-algebra structure,
Yes.
and you want to define it as an sort of an algebra like over operad, that's what you're trying to do because you speak about E1, E2, and so on. But in fact, it's an algebra over a prop, not over an operad, because you have this coproduct and they have to be compatible. And this compatibility is a three-dimensional thing. So I believe that in general, if you want to realize say graded vector, it doesn't matter, complex or object of some DG category. If you want to realize it as a Hopf as a bialgebra, I believe you really need some E3 type of structure. Maybe in this particular case, when you have a 1, E2, that Maurer-Cartan is enough. But in general, it's highly non-trivial. It's related to some non-trivial geometry of 3D polytopes, but I believe
Okay.
E3 is hidden somewhere. But anyway, go ahead, yeah.
Yeah, I'm confused by that, but it would be nice to work it out.
Yeah.
If you ignore the rest of the slide and start with an A infinity algebra and a deformed coproduct like this, that doesn't go from A to A tensor A, but rather to a more Cartan deformation of the right-hand side, and ask what coassociativity means in this case. It implies what look like cabling relations for the more Cartan element, which is why I've called it R rather than mu. So the more Cartan element ends up looking like an infinitesimal R matrix. It's odd, so it should be infinitesimal. It's sitting in homological degree 1. And moreover, looking at triple tensor products, the cabling relations are enough, but they'll imply that the more Cartan element for the triple tensor product, which can be written as the sum of three copies of R in different factors, obeys a more Cartan equation. And that more Cartan equation is infinitesimally Yang-Baxter with further A infinity corrections. And again, this is a thing that I've looked around for and not something I've seen. Okay, so I mentioned all this because the structure one finds in 3D holomorphic topological theories is a chiral upgrade of this. So trying to represent a chiral category, we translate things to perturbative, and we can only work perturbatively because, well, in part because I can't produce boundary conditions in 3D HT theories. And so at least the basic choice one has to produce fiber functors are the perturbative ones that Costello defined initially, using vacua at infinity. And then there's a computation to be done, and it can be done in generality for perturbative theory with a series of arbitrary interactions. And what one finds is an algebra that that starts to look like a vertex bialgebra. In other words, it has a coproduct that's now Z-dependent, that's potentially singular, but that coproduct is not naively an A-infinity algebra morphism, but requires a Mori-Cartan element to be turned into a morphism, and that Mori-Cartan element is also singular. It depends on a spectral parameter. One ends up with an algebra like this. Because it doesn't matter if you have 2 points in a holomorphic plane, it doesn't matter which direction you take OPEs in. It's just a shift of the labels. This little r has to satisfy unitarity conditions and is compatible with translations. And maybe most interestingly, it satisfies a spectral version of the Mori-Cartan, the Mori-Cartan and the Yang-Baxter equations. It satisfies spectral cabling relations and Yang-Baxter. So the claim is that this is the structure that represents, in general, chiral categories. And then I have some examples. So one is free matter. If what I mean by that mathematically is that the category we're trying to represent is coherent sheaves on the loop space of C. And the way we'll represent it is by Koszul dualizing half the modes into odd variables. So like the loop space of C has positive and negative integers worth of like loop coordinates, and I keep the positive ones and I dualize the negative ones to odd variables. And those fit together into the structure of one of these, what we called DG shifted Yangians. The only interesting part is the R matrix, which is a computation in field theory. It sort of uses the shifted symplectic pairing between the odd and even parts here to construct. And everything is graded commutative, so it satisfies all its Mori-Cartan and Baxter and everything equations trivially. The coproduct would have been an algebra morphism even without this R matrix, but that coproduct doesn't faithfully represent OPE of sheaves on the loop space of C unless the R matrix is included.
So quantum R matrix is just exponent of this, since everything commutes, or it's more.
So So this is it. It's infinitesimal. It's an odd homological degree 1 infinitesimal element, and I don't know any meaning to the exponential of it. Like exponentiating homological degree 1 elements doesn't sound like the right thing to do.
No, it's a question, what is a quantum, or if there is an
I have no idea.
Yeah.
Yeah.
It looks as a logarithm, or whatever.
Yeah, absolutely it does. I have no idea.
Okay.
It's and also, like, I'll emphasize again, the coproduct is symmetric, and the Yarn matrix has nothing whatsoever to do with swapping the coproduct to its opposite. It's involved in a completely different operation. And if you want something non-trivial, you can add a superpotential. So here the category, to the extent that it makes mathematical sense, what I am trying to get at is coherent sheaves on the loop space of C, or you could take any affine space with a superpotential that's the residue of a polynomial function W. And so this much of the structure stays the same, in particular the R matrix stays the same. The interesting thing is that they're A-infinity operations, just as you would expect in 2 dimensions when superpotentials are around. And they're like A-infinity chiral operations on these various fields governed by derivatives of the superpotential. And it's a really pretty exercise to check that the Morris-Cartan equation is satisfied and that the Yang-Baxter equation is satisfied. That now becomes extremely non-trivial. The last example I'll mention is gauge theory. And pure gauge theory with a Chern-Simons level in the holomorphic-topological setting is equivalent to Chern-Simons. To fully topological Chern-Simons, it's just being presented in a way that's not obviously fully topological. And interesting things come out. So the category I'm going for, when you keep holomorphic dependence around, can be described as modules for the affine Lie algebra associated to a Lie group G, or Lie algebra G, at some level, and there are shifts around. But I'm looking at modules for an affine Lie algebra, and the way that gets represented is by Koszul dualizing the negative modes. So the affine Lie algebra has generators J for with both positive and negative modes, and I've Koszul dualized half of them. That's one way to think about what's going on. And when the claim is that when you do that, you get a tensor product over vect rather than the horrendous vertex algebra fusion product. And there's a pretty structure in R matrix that controls tensor products. So the algebra one gets involves half of a loop algebra generated by the J's and half of a ghost algebra generated by the duals of the negative modes. It's a DG algebra, and the rest of the structure on it is quite simple. And the R matrix is quite simple. And yes, and so the claim is that with this R deformed coproduct, one is actually getting representations of Kac-Moody. The last nice thing to say about this, in the Kac-Moody world, we have conformal vector that tells us that when we take fusion of modules, the fusion is locally constant. And so the category of modules becomes a braided tensor category. We should see something like that on the Koszul dual side, and we do. We look at the shift operators, and we see that the shifts are exact. And that exactness is how local constancy appears in the representation theory of this thing. Yeah. That was a very quick summary of the holomorphic side of things in 3D.
That's great. All right. So this was the last slide. Any questions?
This is it.
Any questions to Tudor?
Any quick. So then the last slides you mentioned, but this is kind of a DG vertex algebra. Am I right?
Yeah, I mean, it's half of a DG vertex algebra. It doesn't contain negative modes. So, but it's very
So
close.
only the positive mode is so the modes are positive. That means the involving only the inverse of the Z in the formulation here. Yes, it does. So that's is that called the vertex D algebra? Half of that. Am I right?
Yes.
Yes, it is a vertex D algebra. So what I'm curious in this differential, and the parameter Z is still running on the curve, so the Z will have always different on the DG degree is always just degree 0 parameter, right?
Exactly. Yes.
Okay.
Yeah, and
Yes.
actually,
Yes. Absolutely. And that's consistent with the R matrix having
And R matrix, and also this D, and well, the D actually is a differential which does have, but the L is the let me see, that's from Versora.
Yeah. Well, but sorry, we're calling it L because it's a reflection of the conformal vector, but it's a different L. So it's the Koszul dual of the conformal vector.
Okay, but those are all homological. See, here you said that is it's not.
Yeah, so it's a degree minus. It's a degree minus one.
Degree minus one.
Yeah.
Okay, thank you.
Yeah.
And also, Tudor, what you explain, it's sort of a local story. Yeah. If you can you add the global curve and do indeed the full factorization type of construction? Yeah.
It's a nice question. There are certainly things to try. I don't know. I
think I think I thought about that question a little bit. So if you choose smooth modules, your R of Z is just as you can evaluate it as a smooth function on C star. And that's consistent with, no, you can think of this as a sheaf of modules over C star, which is P1 away from 0 and infinity. And that's consistent because this, I think one can interpret this tensor product module as a conformal block, a 2-point conformal block with one puncture at 0, another module set at another point of C, and with some regular singular.
Yeah, and Young-Baxter is a flatness condition because I'm thinking beyond the elliptic, trigonometric, and rational when you
yes.
base.
Right, I think the same. You can write down a similar kind of this meromorphic R matrix for the other solutions of Yang-Baxter equation, and from this physics perspective, they correspond to putting this theory on different curves, and the evaluated meromorphic tensor product should extend on those curves as like they really should correspond to conformal blocks in a derived way. Yeah.
Okay, yeah, it's a good point. Thanks, Andrew. Okay, more questions? Well, if there are no more questions, Tudor, thank you very much for your nice lecture
thanks
course.
so much
It's
for inviting me.
great. It's very interactive and very interesting. Yeah, and nice comments from the audience. Well,
it was nice to chat with everyone. Oh, yeah, I'll see you all later. Thank you, Jan. Thanks, everyone.
Bye.
Bye.